Welcome to This Explainer. Today, we're unraveling the cosmic rulebook of gravitation. You know, it's one of nature's 4 fundamental forces, and it's literally the invisible thread holding our entire universe together.
To start us off, I want you to ponder something for a second. Think about how the exact same force that drops an apple from a branch down to the ground is also the very thing keeping the moon perfectly tethered to Earth in its orbit. It's kind of mind-blowing when you really stop to think about it, right? The exact same thing making you feel heavy right now is what keeps the whole cosmos dancing in perfect rhythm.
So, here's our roadmap for today. We're going to start with the universal invisible force, dive into Newton's law of gravitation, explore gravitational field strength, finally connect big G to little g, and wrap up with how gravity shapes our daily life.
All right, let's jump right in. The universal invisible force, from apples to orbits.
It's really fascinating to trace the historical leap here. So back in the early 1600s, Johannes Kepler did something pretty amazing. He accurately mapped out how planets move around the sun in these elliptical paths. Basically, he gave us the geometry of the heavens. But, well, the puzzle was missing a massive piece. He didn't know why they moved that way, what was actually driving the mechanism. Fast forward to 1687, and Sir Isaac Newton enters the chat with the universal law of gravitation. Newton provided the why. He proved that the exact same invisible force pulling that apple to the grass is what keeps the planets sweeping through the void. It was a total game changer, unifying Earth and space under one single set of rules.
Which brings us to Newton's law of gravitation, the cosmic equation.
Now, we get to Newton's brilliant realization. Every single mass in the universe naturally attracts every other mass, literally everything. Doesn't matter if it's a supermassive star, a tiny grain of sand, or, your morning cup of coffee. The core equation states that this gravitational pull comes down to 2 main things. First, it's directly proportional to the product of their masses, meaning the larger the objects, the stronger the pull. And second, it's inversely proportional to the square of the distance between their centers. Put simply, the absolute size of the objects and the exact distance between them dictate the fundamental strength of this cosmic attraction.
Okay, so take a look at this incredibly tiny number, 6.67 times 10 to the power of -11. This is the universal gravitational constant, or capital G, and it is universally constant, meaning it's exactly the same everywhere. Whether you're standing on Earth, orbiting a distant black hole, or floating way out in the Andromeda galaxy, G is rigidly fixed. Because this multiplier is astronomically small, we're talking 0.000 and so on for 10 zeros before hitting a solid number, it brilliantly explains why you aren't gravitationally pulled toward everyday objects. Like, you and the person sitting next to you absolutely have a gravitational attraction pulling you together. But because your masses are so incredibly small compared to a planet, and G is such a microscopic multiplier, that force is completely negligible. We really only notice gravity when at least one of the objects is absolutely massive.
Let's see how this builds into the inverse square law. As objects move farther apart, the gravitational force doesn't just fade out linearly. It literally drops off a cliff. When the distance between 2 objects doubles, the gravitational force doesn't just halve, it becomes just 1/4 of what it was. If the distance triples, it plummets to 1/9. Think of it kind of like a can of spray paint, right? If you hold it super close to a wall, the paint is concentrated, thick, and intense. But as you pull that can further back, the exact same amount of paint has to spread over a vastly larger area, becoming extremely weak and dispersed. Distance is a massive, defining factor in how strong a gravitational pull will ultimately be.
All right, let's bring it closer to home. Gravitational field strength, the local experience.
We've talked about the universal force stretching across galaxies, but how do we actually measure a gravitational field locally? Well, a gravitational field is simply the region around a mass where another mass experiences a physical pull. We define gravitational field strength, which is known as lowercase g, as the gravitational force per unit mass. Down here on Earth's surface, this pull equates to an acceleration of approximately 9.81 meters per second squared. That's essentially the local grip our planet has on us, constantly yanking every single kilogram of mass toward the center of the Earth with 9.81 newtons of force.
And this leads us directly to the concept of weight. Weight is just the gravitational force acting on an object, calculated as mass times gravitational field strength. So the absolute crucial takeaway here is understanding the fundamental difference between mass and weight. Mass is your actual stuff, a constant amount of matter. It doesn't change whether you're standing on Earth, flying in a commercial plane, or just floating out in deep space. Weight, on the other hand, fluctuates entirely based on this local gravitational field, little g. This is exactly why stepping on a scale on the moon would make you feel like you magically lost over 80% of your body weight. Your mass is identical. You haven't lost any actual matter at all, but the local pull dragging you down is just remarkably weaker.
Now for the really fun part, connecting big G and little g, the aha moment.
We have these two concepts that sound incredibly similar but are vastly different. By juxtaposing the unchanging cosmic constant, capital G, against our fluctuating local reality, little g, we can clear up a massive point of confusion. Remember, G is the same everywhere in the universe. It's a fundamental, unbending constant of nature. But little g, gravitational field strength, depends entirely on your specific location, the celestial body you happen to be standing on, and even your altitude above it. Understanding how one essentially gives birth to the other is the absolute key to grasping classical physics.
So by equating Newton's universal force equation with our local weight equation, we get this beautiful little formula. Little g equals capital G times the mass of the planet divided by the radius squared. Notice what is completely missing from this equation, the mass of the falling object itself. Because the object's mass cancels out entirely, this proves mathematically that local gravity accelerates all objects at the exact same rate, regardless of how heavy they are. This is why in a vacuum, where there's no air resistance, a heavy bowling ball and a light feather will fall and hit the ground at the exact same instant. Galileo famously proposed this centuries ago, and here is the strict, undeniable mathematical proof behind it. Your local gravity depends strictly on the massive planet beneath your feet and your exact distance from its core.
And this brilliantly illustrates that exact concept in action. Think about a 70-kilogram astronaut. Their mass remains exactly 70 kilograms everywhere they go in the solar system. But because little g changes so dramatically from planet to planet, their physical weight plummets from 687 newtons on Earth down to a mere 113 newtons on the moon. That is exactly why we see that light, bouncing walk in the old Apollo footage. On Mars, they'd weigh a bit more, at 260 newtons, and if they somehow found a solid surface to stand on Jupiter, they'd be crushed under a weight driven by a ferocious gravitational field of almost 25 meters per second squared. The constant nature of mass versus the wildly varying nature of weight is completely driven by where you happen to be in the cosmos.
Moving on to our final section, gravity in daily life, the invisible thread in action. One of the absolute coolest practical applications of these formulas is calculating escape velocity. This is the absolute minimum speed an object needs to escape a planet's gravitational field without needing any further propulsion. Essentially, how fast do you need to throw something so it literally never comes back down? Using the mass and radius of Earth that we just explored, we can calculate that a rocket needs to reach a blistering 11.2 kilometers per second just to break free of Earth's gravitational grip. To put that staggering number into perspective, 11.2 kilometers per second is fast enough to travel from New York to Los Angeles in under 7 minutes. Without mastering this exact math, escaping our atmosphere for space exploration or deploying essential satellite missions would be entirely impossible.
And you know, this math is working for us constantly behind the scenes. We completely rely on gravity to act as the exact centripetal force, keeping satellites in a perfect circular orbit. They are essentially falling toward Earth constantly, but moving fast enough sideways that they just keep missing the ground. This delicate cosmic balance powers the GPS navigation in your phone, our global television broadcasting, and our entire modern weather forecasting system. Back down on the ground, we literally harness the moon's distant gravitational pull. It tugs on our oceans, creating the high and low tides. These tides sustain complex coastal ecosystems, guide maritime navigation, and even allow us to generate renewable tidal energy. Even in the realm of civil engineering, calculating precise load analysis against Earth's steady gravity is the invisible math keeping towering skyscrapers standing upright and massive hydroelectric dams safely holding back millions of gallons of water. Gravity is really the ultimate architect of our daily routines.
As we wrap up this explainer, I want to leave you with this defining thought. Gravitation is the universal force that binds the cosmos together. Newton's simple, elegant equations provide a completely unified explanation of how masses interact. It mathematically unites the sprawling, majestic motion of swirling galaxies and orbiting satellites with the incredibly mundane, everyday act of dropping your keys on the floor. It is just one grand rulebook for the entire universe.
So, I'll leave you to ponder this incredible invisible thread of gravity. It's the fundamental law connecting everything, from the apple in your hand to the farthest reaches of uncharted space. How does a single elegant equation manage to bind the entire cosmos together? Keep wondering, keep learning, and thank you for joining me for this explainer.